Now let's come back and solve the most important questions in electron gain enthalpy. That is, why are halogens strong oxidizing agents? So what basically is oxidizing agent? Something like which has an ability to gain electrons, isn't it? So whichever gains electron, it acts as an oxidizing agent. Let's come back and I'll start answering this question. So whenever I have to speak about the oxidizing agent, this particular word is given to you in the exam, I felt this is the way you write your answer. How basically oxidizing agent, what does it depend upon? We have studied in the electrochemical series, that is your the ability to gain that concept, the values of E naught potentials, the electrode potential values will decide whether it is an oxidizing agent or reducing agent. So first important concept you have to write is this property depends upon oxidizing property depends on E naught values. Okay, what way are we relating? We are going to relate with this concept, that is delta G naught is equal to minus NF E naught. We have already, hope you have studied in your classes electrochemistry. The more or the delta G naught value, if it is negative, then automatically E naught value is positive. If the E naught value is positive, that means higher E naught value, that means higher positive value, more is its oxidizing nature, or more is its oxidizing property. Remember this concept first. So we are relating in this term. The next important thing, so I have got more E naught value, or that means positive, that is fluorine, which is 2.34, and iodine, it is very much lesser, that's 0.453 or something. So higher end of positive values I get say it is a stronger oxidizing agent. Done. So the first concept, writing generally, so oxidizing depends upon this. Let's come back and see on what is this E naught value further dependent on. So the E naught value depends upon important parameters. What are they? Let's see. Suppose if I have here, I'm going to take a halogen, done. So halogen atom X2, done. Okay, half of this. Now I'm going to introduce onto this concept called delta. Just see, atomization also I can say. You can say dissociation also. I'm going to dissociate it using certain amount of energy. Minus. So this is the delta dissociation or delta atomization energy, which is used to break this particular atom or the gaseous atom into its element. Just see how am I going to break. Now I'm going to dissociate this. This becomes X gaseous. X2 has become X. So how much am I using? I'm using half of it because to break that. So I'm getting X gaseous atom. Now after that I'm going to introduce or use or supply amount of this. I dissociated it, broken it. Now what will happen from the gaseous atom? I'm going to introduce one electron to this. When I'm using electron to it, that is the process of electron affinity or electron gain enthalpy. So when I'm trying to introduce one electron to this, what energy I'm going to electron Eg delta G Eg electron gain enthalpy minus. How much this will become into X minus delta X minus, because it has gained electron in gaseous state. Now further what am I going to do? I'm going to introduce or convert this into using hydration enthalpy. I'm going to convert this gaseous this in ion in gaseous state into its aqueous state. So this becomes using delta hydration enthalpy delta H minus. This gets converted to X minus aqueous hydration enthalpy. So why am I trying to explain? The electrode potential values depends upon all these factors. So why when I speak in terms of halogens, most important thing you're going to write electrode potential values of halogens. If I see in terms of dissociation enthalpy or the atomization enthalpy, so dissociation enthalpy or atomization enthalpy. So E naught depends upon, this is our first concept. The next concept, what do we say? It also depends upon electron gain enthalpy. Okay, it also depends upon hydration enthalpy. Hydration, this one, hydration enthalpy. Okay, now what are you observing? When I say the dissociation enthalpy of halogens, if I have to see the values, they're very low. When I have to see the hydration enthalpy values, I'll be showing in the next question. Hydration enthalpy values are very high. So what is electron gain enthalpy? Electron gain enthalpy we have already seen in one question. They have maximum negative electron gain enthalpy compared to others. So they have maximum negative electron gain enthalpy. So this, with this reason, I am going to say that the electrode potential value, adding all these values, right? When I add all these values, what value do I get? I get a value where delta G is negative, and because delta G is negative, delta E naught will become positive. When it is positive, it is more oxidizing agent. So please try to answer your question like this. Very important, very clear about all the concepts. Dissociation enthalpy I have shown here, negative gain enthalpy I have shown here, hydration enthalpy I have shown here. So cumulative of all this, addition of all these will give the answer. Let's come back and start this. They said electron gain enthalpy for fluorine is less than chlorine, then fluorine is acting as a stronger oxidizing agent. Why is it acting? Why is it gaining electrons? They want us to write. The same concept I'm writing here, but in terms of fluorine. Now start. So electron or the oxidizing property, same thing. Oxidizing property depends on electrode potential values. So fluorine has positive E naught value, right? So positive E naught value means more oxidizing nature or oxidizing power. That's the first thing. Second important thing, you have to write the same thing. Let us write in terms of fluorine. The first I'm going to take fluorine. Then the gaseous state, I'm going to use delta atomization ATM or dissociation H minus. So how much was this? It was equal to almost 158.5 kilojoules per mole. Then I broke this into F gaseous, into atoms. Done. After this, I am going to use an energy called electron gain enthalpy delta H minus. It has gained one element, electron affinity rather. So then once it gains one electron, it becomes ion. Excess gains electron minus. Now from this gaseous atom, I am going to introduce delta hydration enthalpy of fluorine. Then immediately the gaseous atom gets converted into F minus aqueous. Now when I am going to add all these values, yes, I have observed that the fluorine atom, yes, two important concepts. The same thing, you're going to write the same answer here. What should be the thing? Dissociation enthalpy is low. Okay, I should write hydration enthalpy. Hydration enthalpy was found to be 555 kilojoules per mole. So what is the concept? The dissociation enthalpy of fluorine has low delta atom atomization. You can write atomization means ability to break, dissociate into two atoms. Done. It is 158. And hydration enthalpy is how much? High hydration enthalpy. Hydration enthalpy. Now the addition of the cumulator according to Hess law, we summate, isn't it? So when we summate together, we have got more of negative G naught value, and the E naught value, the electrode potential value was positive. So according to this relation, this is negative, this becomes positive, isn't it? So with this concept, I have understood that fluorine, this is the chart of the Born-Haber cycle which we have shown. And finally, I have concluded because of these two factors, fluorine and this factor also, fluorine is a stronger oxidizing agent than chlorine. You have to end your answer there. Now let's come back and start with the chemical properties of your group 17, that is halogens. So let us discuss one after the other. Then we have already done the general trends, that is your atomic and ionic radii, melting point, boiling point, electron gain enthalpy. I also did questions on electron gain enthalpy, bond dissociation enthalpy. Let's come back and discuss. So in chemical properties of group 17, most important thing, let us start with the oxidation state, because with the oxidation state today we will know which type of compound it's going to combine, which type of element it's going to combine. So basically oxidation state in group 17 elements, if I have to see, like fluorine, because of its smaller atomic size and non-availability of d orbital, so fluorine with atomic number 9, it's going to only show -1 oxidation state. If I see chlorine, bromine and iodine, they are going to extend their valency to, they're going to show further to your 1, 3, plus 1 plus 3 plus 5 plus 7 also, right? So why are they extending? Because of availability of d orbitals. which is absent. So absence of d metals. It is restricted only to P, isn't it? Done. So when I have to come back to reactivity, yes, all the halogens are highly reactive in nature. Let us write. So when do I say something is highly reactive? When the bond dissociation enthalpy, the amount of energy required to atomize it, break it into atoms, would be less. So they are highly reactive due to low bond dissociation enthalpy. This is the concept. And oxidizing power, I already did certain equations in oxidizing nature where I said it is going to depend upon electrode potential values. So electrode potential values again depends upon Gibbs free energy. We have already also studied they are going to depend upon hydration enthalpy and atomization, enthalpy of atomization, electron gain enthalpy. Okay, let us not write everything now. We will generally write oxidizing power means fluorine is a stronger oxidizing agent compared to chlorine, which is oxidizing agent than bromine, which is oxidizing in iodine. That means in the group, fluorine is the strongest oxidizing agent, where I've already given the reasons in the earlier video. Please watch that. And here iodine is the strongest reducing agent. So remember one important thing. The reason also given, watch that. So as we go down the group, the oxidizing nature reduces. Right. Let's come back and see the next type of chemical properties, that is a reaction with oxygen, reaction with metals. We'll be seeing further also. Done. So whenever I have to speak about reaction or chemical properties, you'll be basically asked about the trends in them, right? What am I trying to explain you? So I said the halogen atoms are going to combine with the oxygen atom, that is the by the atom of that oxygen, and forms different types of oxides. Done. Fluorine, as you have seen, is going to form two types of oxides. Here chlorine is going to form these type of oxides, and bromine is also again forming three types of oxides. We will be learning the structures also, and iodine forms I2O5 type of oxide. Now what is the question which is asked by board? What do they want? What is the stability of oxides among all these group 70? That is what they're going to ask you. So when I have to see the stability of these oxides of fluorine, chlorine, bromine, iodine, so iodine greater than your this in bromine. No, what will come first? Basically it is fluorine, chlorine, bromine and iodine, isn't it? Done. After bromine, after iodine is bromine, but here the stability, when you see iodine greater than chlorine greater than bromine, so what is this order? It is a decreasing order of the stability. So this is the strongest, this is the decreasing order. So decreasing order of stability of oxides, which is most, now compare, just see, I said decreasing order, so which is highly stable in its oxide form, this one, which is less stable, this is less stable in oxide form. So when I have to come back to metals, remember carefully, again they're going to ask you order. So when I have to see this in group 17 reaction with metals, the group 17 elements, the non-metal, that is fluorine, chlorine, bromine, iodine, they're going to combine with only monovalent metal. That means only one. It's combining and forming a compound of type MX. So let us write. If it combines with fluorine, it forms MF. If it combines with chlorine, it's going to form MCl. If it's combined with bromine, it forms MBr. If it combines with iodine, it combines. Now what is the board going to question you? Among all these, arrange the following in their decreasing order of their ionic strength. So when I have to see greater, 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 done. So what is this order now? This is decreasing order of ionic strength. Why? Because higher is electronegativity tends to pull the electrons, and there's a formation of ions, isn't it? So decreasing order of the ionic strength. This is the high. This is high ionic strength, and this is least ionic strength. Right. Now let's come back and start with the next concept, that is the reaction with hydrogen. So halogens are going to combine with hydrogen and forms, as we said, in halides, MH or sorry, HX in halides, and in hydrides MH. Okay, let's come back and see what am I trying to explain. So in basically reaction with hydrogen, when we speak, you have to speak in terms of reducing agent or reducing nature of the particular halides. What am I trying to explain? So in the exam, what type of question is asked from this hydrogen reaction with hydrogen? Let's see. Now they're going to ask you question based on their acidic nature. Acidic nature means release of H plus ions. Whenever they're asking you about acidic nature, they'll also be asking you about reducing property, because reducing property is nothing but ability to lose electrons, isn't it? Right. This is one concept. Next, they're going to ask you in terms of ionic nature. Ionic nature. Then they're also going to ask you in terms of boiling point. Okay, let us come back and see the order. Now, when I have to speak about the reaction with hydrogen, I said metal, monovalent metal, right? Okay, and now I have to, okay, now not to speak in terms of metal, I have to speak in terms of hydrogen. So hydrogen is combined with your halogen and forming HX. Now we have all, we'll be writing the hydrogen reaction with halogen with all the halogen. Let us write your HF. So this is and hydrogen plus halogen, HCl, HBr and HI. Now let us write in terms of the order in terms of acidic nature. So what is acidic nature? Ability to donate the H plus ion. Done. When something is donating, that's nothing but the reducing properties in it, loss of electrons. Now when I have to see all this, when I have to write among all this, iodine has the largest size. When iodine is a larger size, which is strongly acidic, iodine is larger size, the bond between hydrogen and iodine is very weak, because the size is larger, and then this breaks up into H plus and I minus. When this HI, the bond is very weak, it can easily donate this H plus ion. When it is donating H plus ion, isn't it highly acidic? When it is donating acidic or it's releasing H plus or hydrogen, that means isn't it reducing property stronger? Once again, the size of iodine is larger compared to fluorine. When the size is larger, bond among hydrogen and iodine is weaker. When the bond is weaker, it can easily donate proton, which is acidic in nature, and indirectly when it is releasing proton, I say it is highly reducing in nature. So let us come back and write the order now. When I have to write the order, among this, fluorine is least acidic, then chlorine least acidic, then bromine least acidic. So HI is the strongest among all reducing agent, and this is oxidizing agent, which we have written already. Now let's come back and write ionic nature. Again the same concept. Among all these, when I have to see the size, then HI, the size is larger. HF, the size is smaller. When the size is smaller, it tries to hold, because of its electronegativity, it tries to hold, or it's going to pull the ions in this way. It's going to break the bond. When the bond is very strong enough, when it's breaking bond, this gets a positive charge, this gets a negative charge, isn't it? So which is strongly ionic in nature? Indirectly, if I write HF, it is greater in ionic nature than HCl, greater ionic nature than HBr, greater ionic nature than HI. Remember that. So this is the strongest ionic character, this is the strongest reducing character. That. Let's come back and write boiling point. Here you have to remember a bit different. How is the order? It is first HCl, then it is HBr, then it is HI, then HF. Remember this order please. Then according to based on their the bond dissociation enthalpy. So here HCl is lesser than HBr, lesser than HI, lesser than HF. This is the order for boiling point. So how should you remember? Acidic character, you have to speak in terms of size and ability to donate proton. Ionic nature, you have to also speak in terms of electronegativity, because of the electronegativity will drag and form two poles, polar compound, plus and minus. Done. Ionic character is more. And I have to speak in terms of boiling point. I'll speak in terms of atomic size, as well as that atomic or interionic attractions in between, the attraction in between them, and the bond dissociation enthalpy also. Remember that. So boiling point, this is the order. Please note this order. Done. So let's come back and see. What are interhalogen compounds? When one halogen combines with one more halogen, right, then we call it as interhalogen compound. We'll be learning the different preparations also, but as of now, remember, group 17 elements are going to form different interhalogen compounds in this way. So if I have to write X and X, what is the thing? N. I'm writing this. N can be how much? Just see, N can be 1, right? N can be 3, N can be 5, N can be 7 also. With one halogen combining with so many, like the different halogen, which can range from 1, it can range from 3, it can range to 5, it can range to 7 also. It's a combination with two different halogen atoms. So in this topic, if you have any doubt, please let me know in the comment section.